This is my discussion of the Unit 2 dynamics for multiple choice. Unit 2. Number 1 is in which following is the object's direction and kinetic energy, direction changing and kinetic energy decreasing. In A, in order for kinetic energy to decrease, work equals the change in kinetic energy, the net work. This work has to be negative in order for the kinetic energy to decrease. And that means that I have to be in between an angle of 90 to 180. 90 degrees is zero work. So this is no delta KE in this situation is zero. I do have a net force. This is changing the direction, but that's what's actually will cause that velocity vector to change and curve upwards. So in A, that is not correct. In this situation, I do have a change in kinetic energy that is negative, so I'm decreasing, but I'm not changing direction until it comes to a stop. And this is at the instant shown. So I would have to come to a stop and then I would change direction. This delta KE is positive. I am going to also change direction, but I'm increasing. Delta KE in this situation is negative and I'm changing direction. Number 9, we can do number 4. This bus is turning to the left. I want to look at a box that is inside here and starting to slide to the right. And we want to know what would best represent all of the horizontal forces acting on the box that start sliding. So it was at a constant speed. This is constant. And the only thing that would be acting on the box would be friction, and that would be B because it would be trying to oppose motion. There's no other forces that are acting on the box. A 50 kilogram box, I'm sorry, a 50 Newton box, that is 50 Newtons, which is its mass times G. So I can figure out the mass of the box, but that 50 Newtons is its weight. It's at rest on a horizontal surface. So here it is. The coefficient of static friction between the box and the surface is 0.5 and the kinetic friction is 0.0. I'm going to apply a 20 Newton force and we want to know the acceleration. Well, we got to figure out whether or not this is large enough to overcome the force of static friction max, which is equal to mu s times force normal. And force normal is equal to its weight, or Fg, which they gave us. So mu s is 0.5 times its weight, which is 25 Newtons. And therefore, this force is not overcoming it, okay? So I am located somewhere approximately here on that curve. And so I am not moving. A crate is on a horizontal surface. A force of magnitude F is on the crate. It slides some distance. F is kept constant. And now we double the angle, okay? We want to know how the new normal force is affected. So let's draw a free body diagram. We have force normal. We have F. We have Fg. We have sliding. Do we have friction? Causing the slide, right? Doesn't matter if we have friction or not. Nope, there's no friction. It's frictionless. Okay, so this is F cosine theta, and we have F sine theta upwards. All right, so we want to know what happens when force normal when I increase the angle. So I'm going to sum the forces in the y direction, set it equal to 0, and solve for force normal. I know that force normal is equal to Fg minus F sine theta. I skipped a bunch of steps there. Sum the forces in y, they're equal to 0, and add all the forces up. If I increase my angle, sine theta becomes a larger fraction. that means the force normal goes down. So the new normal force is less than the original. Okay. We've done this one in class. They wanted to know about the magnitude of the force on the top box, on the bottom box in all cases. Newton's third law pairs, no matter what, those two forces will be equal to one another, whether we are accelerating or not. In every case. This situation is such now that we're moving at a constant speed. We want to know which of the following best represents the forces exerted on the bottom box. They define what all the things are up here. So I have the bottom box. So if I look at the bottom boxes, I have to have force of gravity and a force from the top box, okay? And then I have to have force normal from the floor. Okay, so these two, all right, so now, and if I have constant speed, all of these added up to this have to be equal. So this one doesn't have the correct forces, doesn't have the correct forces. This one is the only option because the two forces, FG and the top box, are pointing downward. Assume the elevator has an acceleration upwards of A. Consider the stock that has two boxes of mass M. So we're looking at this box right here. What is the magnitude of the force exerted on the top box by the bottom box? Top box. Looking at the top box. So here's the top box free body diagram. I have force of the bottom on the top, and that's what we're solving for. And the only other thing I have is FG pulling down on that one. I sum the forces, it's equal to the mass of the top box times acceleration of the top box, which is equal to force of the bottom on it minus FG. I can solve for the one they're asking for, and I will get these two added together. So it's yes. Okay. They just factored out the mass. Okay. All right, let's move on. We did this one in class. It ends up being, I have to pick two, force normal, which is the wall. And we find that, which of the following, and I forget which one was the second one. I've got to find it. C. And we have force normal. We have this F times sine theta. We have F cosine theta. We have FG, and we don't know which way force of friction is because we just don't know because they didn't tell us. So if we solve for all of those, we will find that we can sum in the Y and we can sum in the X. And that's how you get those two answers. Number 48, the students have determined already the gravitational mass. How you can determine that has to do with force of gravity equals mg. So any way that I could determine gravitational mass. They want to figure out a procedure that would allow them to compare to the inertial mass. Inertial mass has to do with acceleration. I have to measure the acceleration of with a known force to define inertial mass. A is a procedure for finding gravitational mass. B is a procedure for finding gravitational mass. C, this is a spring 2 pi m over k. This has to do with the inertial mass. And then this one is using a sensor. They measure acceleration. That's inertial mass. They already had gravitational, so they didn't need it. In order to compare to inertial, they had to measure inertial mass. Number 7, we have to do some free body diagrams. We have force normal. We have FG. We have FG sine theta down. We have a force of friction. We also have a force applied. This is force cosine of phi, and we have that force sine of phi. And so we can find the magnitude of the net force, which will not be in, oh, this is FG cosine theta. In the y direction, it's equal to 0. The only location I have a net force is in the x direction. You sum those two and you will get this one right here. We have a ladder that's leaning against a wall. They wanted to know what following forces have the same magnitude as the frictional force exerted by the floor on the ladder. That is located right here, force of friction, because it's trying to slide left. I'm only really concerned about the forces in the x direction now. And the only other force in the x direction is the force normal by the wall. There is one by the floor as well. I don't know if there's friction here or not. Doesn't matter, because it would be either in the x or y, or in the y direction. And all I care about is what is equal to this. And that has to be force normal from the wall. That would be C. This is a Newton third law pair. They tell us that this force by the tractor is the same in every situation. That means that the force exerted on the tractor by the object is the same. So this is F and this is F. And so the magnitude, let's see, if you read the whole problem, the magnitude of the force exerted by the object on the tractor is equal, because the tractor exerts an equal force on every object. That's a Newton's third law pair. Person's running on a track. What propels the runner forward? So here's his foot, right? Here's his leg. This is the ground. What's actually propelling that person forward is actually the foot force. The foot's trying to slide. And so what's happening is there's a force of friction that's opposing the sliding motion, and that's by the ground. Force of friction exerted by the person on the ground. No. Force of friction exerted by the ground on the person. All right. Number 3 from 2016. We have a situation where I have a block or some object. I have initial velocity of some number. I have a final velocity of 0. I slide some distance, and they want to know the magnitude of the force. 2 ways to approach it. You can use kinematics or you can use energy. Kinematics, if I find the acceleration, which I have enough information because I have 3 things, so I can use 5, 4, 3, 2, 1, find acceleration. So I would have to, I don't know time, so I would have to use final velocity squared equals initial velocity squared plus 2a delta x, which is that d value, which we know. And so we would solve for acceleration, divide by 2 and delta x. So for each one we could solve. And so velocity squared, I'll use the first one, which is 10 squared over 2 times 6.1, and you would find the acceleration. Then if you know the acceleration of the object and you know the object's mass equals 1,500 kilograms, you know that the sum of the forces equals ma, and so they want to know the braking force, which is the only force. You can plug in the value you just found, and using the mass, you can find the force that was used to do that. It's something like 12,200 or something. I can't remember exactly what it was. That's one way. The other way you could do is that we know that there's being work done by the braking force. It's having an effect, and it's changing the kinetic energy. The final kinetic energy is 0, and the initial kinetic energy is 1/2 the mass times the velocity initial squared. What is work equal to? The force that they're asking for times distance. The braking force is in opposite direction, so that will be negative. And we have 1/2 mv initial squared. You can solve for force that way by plugging in the initial velocity and the distance. Again, you will find that it is approximately 12,000 newtons for each case. I would do 2, and then I would move on. Number 31, we have 2 boxes. They're sitting on an elevator. Which of the following ranks the forces in order of increasing magnitude? And they tell us FA is the magnitude of the force exerted on box A by B. FB is the magnitude of the force exerted on box B by A. Newton's third law of pairs say that those have to be equal. I'm going to go and eliminate every single one that doesn't have that. So A, this doesn't have it, this doesn't have it. Notice this has it and this has it. But we also know that it is slowing down. So it is accelerating downward. So I can't have it equal to FG or it won't be accelerating. It's got to be less than FG, which is why it's slowing down. We've done this problem, the next one, many times in class. It was on a test, actually. I think it might have been on the final for first semester. I have a situation where this is at rest. Here is the free body diagram. I have force normal. I have FG. If it's at rest, then there must be a force of friction. It's static friction. And we know we have FG sine theta down the ramp. And we have FG cosine theta that's what your force normal is equal to. What people tend to do is if it's at rest, they say, well, it must be equal to, if they want to know about force of static friction, mu s times force normal, which is mu s times mg cosine theta. I got that from here. This is wrong because we weren't told that it was slipping, okay, or about to slip. So we know for a fact that it has to be equal to FG sine theta. Okay, we don't know where it is on this curve unless they told us it was about to slip. This table value is my maximum. So it is equal to mg sine theta, and that would be C. And notice A is the one that most people, if they're not understanding force of static friction, would get. Now I have to look at it on the way up the ramp. And I want to know the force of friction that's exerted on it, and it's sliding up the ramp. So this is kinetic friction, So that is mu k times force normal. So I got to go over here. I have that's equal to 2 mu k is what they told me. Force normal again is mg cosine theta. And so here is my answer, 2 mu k mg cosine theta. Those were the multiple choice that I gave you from Unit 2.